So far we've introduced the idea of voltage, and I'd like to take just a brief interlude to introduce what might at first seem to be a bit of a screwball unit that physicists like to use to express energy. And we call it the electron volt, which is a little bit of a misnomer, but follow with me here. So usually write it as a little e and a big V like that. And usually we just say EV. Now this E here is the fundamental quantum of charge. So that's why I said it's a bit of times 1 volt. So the reason this is a bit of a misnomer is we should really be calling it something like the fundamental quantum of charge volt, because after all, the charge on the electron is minus E, but we don't do the minus sign. But it's literally just defined to be the quantum of charge times a volt. We can work through how many joules this is. The quantum charge is 1.6 times 10 to the negative 19 coulombs. And a volt, remember, can also be written as 1 joule per coulomb. So this is just a handy way of writing 1.6 times 10 to the negative 19 joules. So this turns out to be a typical energy scale in atomic physics. Energy levels of atoms are handily expressed in ranges between, say, maybe 1/100th of an eV up to maybe about 100 eV, just to give you a nice range. And so when you can deal with numbers that are, from 1% to 100, that's certainly a lot more convenient than carrying around an awful lot of scientific notation. But it's actually even a little more convenient than that. The whole point of this E here is to cancel off against the fundamental quantum of charge without ever having had to substitute the number. So let me just work through an example of how we might use this. So let's say you are designing a device called an electron gun. Which is used in certain kinds of atomic physics research, like collisional atomic physics, where you literally go and throw electrons off of things and see how they bounce. Now, where you get your electrons from will be some little filament right here, just like filament in an old style light bulb. And you just pass a small AC current through it to get it hot. When you get it hot enough, occasionally an electron that's stuck in the filament will decide that it wants to leave the filament. And then that's the role of these two plates here. So I've got a plate here, and I have another metal plate here, this one with a hole drilled through it. And then what you do is you hook this up to either a battery or a power supply. And believe it or not, in atomic physics, a lot of times we use batteries because the voltage coming off of batteries is so stable. We'll get in a little later how batteries work. But for now, we'll just say that they are devices that can maintain a constant voltage across two locations. So this would be the negative terminal of the battery. This would be the positive terminal of the battery, like so. So that's going to make this plate negatively charged. And what we had was an electron flying off the plate, like so. And this plate will be positively charged. Since this is hooked up to the positive terminal of the battery, this will be a higher potential. This will be a lower potential over here. And we know that the electron will want to go away from negative things and towards positive things. So the electron feels a force to the right. That must be then that the electric field is pointing to the left. We'll do more with that in a bit. But anyway, most of these electrons that come off of our filament. Most of them will be accelerated, will strike the other plate, and will be completed through the circuit. But occasionally one of these will fly out the little hole and go flying down to your experimental target. And so what I'd like to figure out is, what is the final speed of our electron? When it comes off the filament, usually the way you've got it set up, the electrons are basically coming off at rest. And we'd like to express the final speed as a fraction of the speed of light. The symbol for the speed of light is c. And the reason for doing that is, a lot of times when you're doing these kind of things, what you do is you do a classical calculation like what we're learning to do now, and you hope that at the end of the day you get an answer where things are moving relatively slow compared to the speed of light. If they aren't, then you have to go back and redo the calculation, taking relativity into account, which is more tedious. So you can do this by energy conservation. You can go ahead and make yourself a little table like we were before. So final, initial, and so we can write down kinetic and electric potential energy. And so we can say that the final potential energy was 0 and the initial was E delta V, where delta V was our voltage. Let's go ahead and make that 1,000 volt difference. Our final kinetic energy is 1/2 m little v squared, and the initial is 0. So you go ahead and you just solve this the way you would before. E delta V, and you get that the final speed is the square root of 2 E delta V over m. Now here's where the magic comes. You don't substitute in for the E. You just leave it there. We'll put in our 1,000 volt potential difference. And then when you substitute in the mass of the electron, I promise you, if you go ahead and do all the unit conversions, it'll work out. But you can look it up and you can find it in any table. Masses will often get expressed as EVs per speed of light squared, like this. In the case of an electron, it's 511,000 EV per speed of light squared. You should go ahead at some point and do the unit conversion to convince yourself that yes, this really is indeed a unit of mass. So why did we not substitute in the E for the fundamental quantum of charge for our electron? Well, that's because this E in the unit is the fundamental quantum of charge. So you can cancel it without ever having had to write down the annoying number. Volts cancel, and we're left with 1 over c squared in the denominator, so it'll be c squared in the numerator. Take the square root, that's c. Hey, that's doing pretty good. We're going to end up with some percentage of the speed of light. And when you put this through your calculator, you'll get that it's 0.0626 c, or 6.26% of the speed of light. And if you're an atomic physicist who is using this to design an experiment, you breathe a bit of a sigh of relief, because then you know that you don't have to go and do any more relativistic calculations. Alrighty, so in the next video, we're going to go and take a look a little bit more at the relationship between electric potential and electric field, and the working example we will use for that is a parallel plate capacitor. Catch you over there.